Hello, this is Math 676. This is my second presentation from Chapter 4. I'd like to try to do two things in this presentation. First, I'd like to show that the field extension Q adjoined fourth root of 2, comma I is a Galois extension. And secondly, I'd like to show that the Galois group of that what it is in terms of its images of the fourth root of 2 and I by talking about its associated minimal polynomial x to the fourth minus 2 and finding the Galois group of that. First of all, recall that an extension, like in part A, will be Galois if its a splitting field is a separable polynomial. Since we're working with the field Q, we know that all of our polynomials are going to be separable. We need to show that it is normal and separable, and normal here would mean that we need to show that the polynomial we're working with in the extension field, that all of the roots of that minimal polynomial are in the extension. That minimal polynomial would be x to the fourth minus 2. For the first element, it would be x squared plus 1 for the second one, or we can do it together and get all four roots from x to the fourth minus 2. If we just do this, for this one, we would get the roots of plus or minus the fourth root of 2. And here we would get the complex roots plus or minus I. We could separate this into four factors: x plus the fourth root of 2, x minus the fourth root of 2, x plus I fourth root of 2, run out of room here, x minus I fourth root of 2. So we've split it completely into linear factors over Q adjoined fourth root of 2, comma I, and all those roots are in the field, so we know that it is normal. To be separable, we need to ensure that the roots of the minimal polynomials are distinct, and all four of these roots are distinct, so we have covered the separability of it. With that taken care of, we can talk about the Galois group of this extension, or more directly here, the Galois group of x to the fourth minus 2. And it should consist of the automorphisms on the extension field Q adjoined fourth root of 2, comma I that preserve the base field Q. And from the theory, the Galois theory, TFGT, the degree of the splitting field should equal the order of the Galois group, and we can find the degree of the order of that Galois group by finding the degrees of each one of the minimal polynomials. So the degree of x to the fourth minus 2 would be 4, and the degree of x squared plus 1 would be 2. That would take care of, Q adjoined fourth root of 2 and I for the other one. And the product of these two would equal the order of the Galois group. So the order of the Galois group should be 4 times 2, or 8. That should be the order of the Galois group. It's the product of the degrees of the two extensions and the minimal polynomials of those. Now, we don't know exactly what the Galois group is, but we do know its order is 8. And we'll know that the Galois group is a subgroup of the symmetric group of, in this case, 8 elements, S sub 8. So G is a subgroup of S sub 8. And we can refer to that. It would fit nicely with the permutations for these automorphisms with D sub 4, the dihedral group, which has 8 members in it, to cover all those possible automorphisms, different compositions where we are going to do rotations and reflections of a square, the symmetry of a square. It should be isomorphic to that. And to simplify this, I'd like to list those symmetries here. Let's let alpha stand for the fourth root of 2. And we'll let negative alpha be the negative fourth root of 2, and so on. And I times alpha be I times the fourth root of 2. And negative I alpha be negative I fourth root of 2, which would make it easier for us to list all there should be 8 possible permutations here for these automorphisms. First, I could do the identity, which is fixed here, where all the elements are going to remain, the identity permutation of a square. In this case, that would be alpha and negative alpha, and I times alpha, and negative I times alpha. Then we'd like to rotate this. We're going to do all, rotations of 90 degrees or pi over 2 clockwise here. So the first one will be, I don't know what happened here. I lost my pen. 90 degrees rotation clockwise would give us the following. I times alpha and alpha, negative I times alpha, and negative alpha. Negative alpha. I could do 180 degree rotation, producing the following permutations here. Negative alpha and alpha, negative I times alpha, and I believe I times alpha. There we go. We have to have all 4 of them covered. We're going to get all possible combinations here. We could do a 270 degree rotation. And let's see, 270 degrees. That's going to give me negative I times alpha and negative alpha and I times alpha and alpha again. And then we have to do some reflections here. So let's do the horizontal reflection here, reflection about a horizontal axis. A little abbreviation here. Reflection about a horizontal axis, negative I times alpha. And I times alpha, I think, is going to happen here. Yep. It'll be next for the mapping. And negative alpha, and finally alpha. And then we have a vertical reflection about a vertical axis. Let's see, that should give us negative alpha and negative I times alpha and alpha and I times alpha. Got 2 more, and that would be the diagonal reflections here. So from top left, I have a little problem with the screen if I get too low on the screen. Top left to bottom right diagonal reflection here. That's going to be negative I times alpha, then negative alpha, I times alpha, and alpha. And finally, the other diagonal from top right to bottom left. So we got I times alpha for this. This should be the final of the 8 permutations here, reflections, rotations, however you want to refer to them. Got a negative alpha for the end. Now these mappings correspond to the permutations of the roots induced by dihedral group 4, the symmetry group of a square, and these are the 8 elements of x to the 4th minus 2. And that should cover it. All right, that's my presentation.